Hi everybody, welcome to another video in linear algebra, section 1.10, linear models in business science and engineering. Actually, we don't only have a few applications in this section. Right. The first one is about electrical networks. So first, current flow in a simple electrical network can be described by the system of linear equation. A voltage source such as a battery force a current electron flow through a network, and the Ohm's law. So the Ohm's law says that the voltage equal to R times I. R is called the resistance, and the unit is ohm. So we have R in ohms. It's called the resistance. And I is current. The unit is amperes. And then V is voltage. Denoted by volts. The system of linear equation will be the system of equation of I. Shown here, when we set up the system equation in this simple of the electrical network, it is the equation of the currents I. Right, and the Ohm's law say that the voltage is equal to the resistance times the current. Right, and then the Kirchhoff voltage law, the algebraic sum of Ri voltage drop in one direction around a loop equal to the algebraic sum of the voltage source in the same direction of the loop. That means, of course, I will explain that in the more practical way when we can do that to the problem. Right. So first thing we need to know is V, the voltage, is equal to R times I. And the second one is that going around the closed loop, the voltage is going to be 0 around a closed loop. Let me write that out. Okay. I just say around a closed loop. Sum of all the voltage is equal to 0. And of course, some of them is positive, some of them is negative. Well, we will talk more about that later. Depends on the direction. It could be positive, could be negative. But the sum of all that around a closed loop is equal to 0. Of course, in physics, that could be taught as potential. A potential different between 2 points, like between the battery, there will be a potential difference between 2 points. However, if we just have the point, there's no difference between 2 points. So that's why the voltage is equal to 0 in that case. Right, so one thing we learned about that Ohm's law, and then Kirchhoff voltage law will be this. And then one more thing, remember the problem with the traffic on the incoming current in this case will be equal to all the outgoing current. So I should put that somewhere. So this is so I just say sum of currents in equal to sum of currents out. So we have this important thing, important facts 1, 2, and then 3. We can use this 3 to set up the system of equation. The system of equation will be in voltage. However, the variable in this case will be currents. The current is the variable. Right. So we have those three facts. Now the most important is how do we determine the positive or the negative. Now this is called a resistor. It will produce resistance to a current. So this is called a resistor. This is the symbol in the US system. Of course, in the Europe, and they might have different symbol for that. And also in US, this is the symbol for the power source. The good thing of that is about the battery. The longer one is the plus sign, and the shorter side is the minus. And the resistor usually, the resistor, there's no direction on the resistor, so we don't know. So we just have to assume that, let's say if the current going this way, but on this one we do not have to assume. The direction from the power source will always go from the positive to the negative. And it goes from negative here to positive, so it will be a loop, positive to negative, and between them negative to positive, and just go around in a loop like that. Of course, this I just wrote some simple thing. There may be all the electrical device, could be a resistor, could be a light bulb or something, but I just say that go from positive to negative, and in between them negative to positive. That is always the case. Now, for the resistor going through that, we don't have the direction, but let's assume that it go this way. Let's assume that if I go that way, if the current, some other books they use lowercase, here I just use uppercase. If we go against it, we're going to gain the voltage. If we go with the current, because we hit the resistor, even if we go with the current, it will be minus IR. So if the current go that way, if we want to go against it, it will be plus IR for the same direction, the minus IR. And direction of I is just we assume, not with the power source. Now put all of that together, determine the currents in the following network. So let's say we have this network. How do we do? Right. So remember three facts. Sum of currents in equal to sum of current out. The voltage equal to R times I. Determine the direction by this two rule. And number three, around a closed loop, sum of all voltage equal to 0. Now, by the way, when I look at the textbook, the way they do that is very confusing. What I have to find some other example, so it will be easier. And maybe when you look at the engineering book or a physics book, this is close to what you see in there. Right. So we have to have some current. By the way, also a common practice in the electrical network is they put some lower scale letter like A, B, C, D, E, F. So when I say A, B, E, F, we know what loop we're talking about. Or in the loop E, B, C, D, or we talk about the not B, not E. Right, so that's just a common practice of doing this kind of problem. Now, assign a current. When we assign current, the direction original we don't know. It doesn't matter. We just say it goes some certain direction. Right. So it will be three current. Now, by the way, If we're talking about the first loop, the current will not change when go from E to F, from F to A, and A to B. Those will have the same current. So think about the current of, let's say, the water flow. If we just have one straight path, the current will be the same. Now if we have the split, they will not be the same. On the first one, and then the incoming and the outgoing, they will be different. So in this case, this problem, there will be three current. I use the marker to denote that. So the first one, let's say go from here to there and to this, and we assume that it go in this direction. So go clockwise. So that is a current on the first part. The second, and then we say this current in the loop BCDE let's say it go this direction. Then we have the same loop, because from B to C to D to E, there's no split. It just go in one direction. There's no split, so there will be the same current. So this is I3 go in that direction, and I1 go in this direction. So I1 and I3, and then in the middle one, of course, it's I2. So should we go, say, up or down? Right. So let's say it doesn't matter. We can just choose. Let's say go this direction. So we have I2, I3, and I1. Like that, right? This have the same I because there's no split, just one path. There's a split here, so that's why it will be different. So the first fact is the sum of currents in is equal to the sum of currents out. So the first equation is look at the not B. So the current in is I1, the current out is 3 and 2. So at the not B, what we have is I1 equal to I2 plus I3. Because I1 coming in, I2 and I3 coming out. So that's first equation. Right, so we have three variables here, so we have to have about three equations. We should have three equations, so solution have a chance to be unique. Right, so that. Now we look at the loop. The first loop is A, B, E, F in that direction, which is clockwise. So the first one, now for loop A, B, E, F. Now we can start anywhere, but let's just start at A. Now we start 8, go in this direction, we hit a resistor. Is that the same thing as I? If we go from A to B, of course, if we want to go from B to A, that is against the current that we established. We established I want to go clockwise. So since we go with the current, that's going to be a plus. I'm sorry, if with the current, it's going to be minus. So the voltage, the net voltage have to be 0 around the loop. So from A, go through the resistance, we're going to have 5 minus 5 ohms times the current I1, right? Because we go with the current, that's minus. And next, we hit the power source. But this is against the power source. If we go in that direction, that would be plus 120. But since we go against it, let's say, if we go with, it's going to be plus V. If we go against it, minus V. So we're going to have plus 120. I'm sorry. Go from A to B, and then we go against it. Against the power source. Minus 120. And then we go to I2. Is that the same with the current? Yes, if we want to go a loop A, B, E, F, we go in that direction. Against the power source, minus 120. Go with the current through this resistor. So with the current, that's minus 10 times I2. And then here there's nothing. And then we go with the power source. With the power source, that is plus 40, and that equal to 0. The sum of the current in a closed loop have to be 0. A, B, E, F is a closed loop. It's going to be 0. Once again, same thing in the current. Subtract 5 times the current. Go against the power source. Subtract 120. And then go with the power source. Plus 40. Right, that is the loop A, B, E, F. Now look at the different loop. B, C, D, E. We start from B. The current here go that direction. So we go with the current, meaning we're going to subtract 20I3. And then this direction, notice we go through the battery in the correct direction. Direction of the battery is within the battery from negative to positive, and then on the outside positive back to negative. So from here, that is the direction of the battery. So we go the same direction of the battery, plus 80. And then here, go in the direction with the direction of the current, hit the resistor, minus 3, minus 30, I, 3. And then here we go against the current, because that is the direction that we go, and this is against I2. So we're going again 10 times I2. Again, if we go with the current, we lose the voltage. If we go against it, we gain. Go through the resistor. And then next, if we go this direction, B, C, D, E, the closed loop, A, B, E, F, A, that is a closed loop, and B, C, D, E, B is a closed loop. So should be closed loop. Right, where we B, C, and now we plus 10 I2 because we go against the current. And now is this the same direction of the power source? So that's plus 120 equal to 0. Now we have 3 equations, which is good. Now move everything on one side and simplify. We should have the system of equation as follow: I1 minus I2 minus I3 equal to 0. And next, negative 5I1 minus 10 I2, negative 100 plus 40, that is 80, negative 80, sorry, negative 80, move to the other side, that's positive 80. Yeah, negative 80, move to the outside, that's 80. And next, there's 2 of them here, so to combine these terms, negative 50 I3, but first we have I10 I2. minus 50 I3 and we have I3 and I2, that I mean 80 and 100 20, so that's 200. Always equal to negative 200. Right, so I'm going to put this in the augmented matrix. Zero, 10, negative 50, and negative 200. Reduce for echelon form. Right. Actually, just leave the fraction. Right, so we have I1, I2, I3. So in this problem we have I1 equal to negative 3.5 amperes, I2 negative 6.25 amperes, and I3 is 2.75. So they say why sometimes negative, sometimes positive? Well, because originally we say the direction is this way. If it's negative, if we want it to be positive, turn the direction backward, then that should be positive. If originally we say this is going this way, our answer would be positive. So that's all we have. Again, we use those facts, and it's important to know to denote the direction, right? So look at another example. Right. So this again, let's just assume that some currents flow this way. This will have the same current. Let's say it goes this direction. That is I1. Yeah, going clockwise. Again, just put some knots here. The reason I don't make any more complicated knots, because if we have more knot, more resistor, there will be more variables. I just want to have something that's simple enough, and just to get the idea. Right, so that have the same current. Now this will have the same current. Again, we can choose any direction. The last one we say it's going down. Now let's say this one going up. That I2 and I3 will be the other. All of this will have the same I3. Yeah, I3. Let's say this direction. Right, so yeah, both of them clockwise, except I is going up. Right, so first we look at a knot, either knot E or knot B. Let's look at knot B. What do we have? I1 come in, I2 come in, I3 leaving. So I1 and I2 coming in will be equal to I3 coming out. And then next, look at the loop on the left and the right, and then the right. So the loop A, B, E, F, back to A. Right, let's start from A. Okay, let's start from A. We go with the current, so it's going to be minus 60 times the current I1. And then next, we go against the current at the resistor of 20 ohms. So we're going to plus 20 ohms times current I2, because we go against the current. And then next, we go against the direction of the battery. So that's minus 10 volts. And then back to A. And then from A to here, the same direction as the power source, that plus 30. And back to A, we complete a loop, so the voltage back to 0. In the closed loop, that will be 0. Right, that's the first loop. And now look at the other loop. B, C, D, E, B, B, C, D, E, back to B. Right, there's nothing here. Now we go with the current, go through the resistor. So that minus 10 times I3. The voltage is 10 times I3, but with the current, that minus. And go with the power source here, that's the plus 10 volts. And now with the current, go through the resistor, that minus 20 I2. Because that with the current, that will be negative voltage. And that gets back to B. So complete a loop that equal to 0. Right. Now we write the three equations as a system of equations. Move everything on one side. I1 plus I2 minus I3 equal to 0. Minus 60 I1 plus 20 I2. That 20 move to the other side. Negative 20. And then last one, negative 20 I2. Negative 10 I3. The 10 move to the other side is negative 10. Right, put in the augmented matrix, reduce to echelon form. Of course, we can just reduce all the zeros to simplify the equation. reduced for echelon form. One, -1, -1, -60, 20, -20, 0, -20, -10, -10. Right, and we have that. So I1, I2, I3, the pivots. So this problem we have I1 is 0.4 amps, I2 0.2, and I3 at 0.6. Now, so what we amperes. So what we have here is all of them are positive, which means the direction we chose earlier is correct direction. Right. I think those two examples are enough for the electrical networks. Next we have different equation. Right. So what we have is in many fields we need to write the system that change over time, and let's say somehow we have x0, x1, x2 correspond different point in time, and if there's a matrix A such that x1 is equal to 8 times x0 and x2 equal to 8 times x1 and so on, xk plus 1 equal to 8 times xk. So to get from this one to the next, we just multiply a matrix to it, and we just keep doing that. If there's a case, we call that a linear difference equation, or just recurrent relation. So we have an example here. Suppose that demographics studies show that each year 5% of the city move to the suburbs, and then 3% of the suburbans move back to the city. Initially in 2021, there are 90% of population in the city and 10% in the suburbs. Write the relation. Right. First, let's draw a matrix. Right. Let's say there's a city and then the suburbs. Then city. Right. It says that 5% of the city will move to the suburbs, and then 95% will remain. So from the city, 95% will stay. I should say 0.95. %of the city stay in the city, and 5% of the city go to the suburbs. For the suburbs, 3% go to the city, and 97 remains. Right. Right. Now, in 2021, so there will be, in 2021, there will be the population is 90% in the city and 10% in city and 10% in the suburbs. Right, so this is in 2021. Now, of course, the way we set this up is in 2021 is this. So in that case, when we set up this equation, let's say in 2022, how do we do 2022? So this is in 2021. That is what we have. Now in 2022, what we have is, so we're going to take this matrix times that, and now let's write it first, and then I'll explain why it makes sense. So from city to suburbans, and then city suburbans, and then multiplying whatever equal to, that will be in the city and in the suburbans. Right. Now multiply row times column, row times column. So the first one, so square space. The first one, row times column, rows times column. So we have 95% of the city times the population at the city at the moment. Plus 3% of the suburbans will move to the city. And at the moment, only 10% of the population is that. So when we add those up together, we have the percent of the population at the city. Now, if we do this 0.05 times 0.9, meaning that 90% of the population at the city and 5% of those population at the city will move to the suburbans, and then 97% of the suburbans times 0.1. So 1%, I mean 10% of the population and 97% of those 10% will stay in the suburbs. So in that case, we will have this. So in general, we have the relation is that let x be the percentage of x at the city and the suburbans. And that will be at time k. So this is this is c k s k. So this is the proportion of the population at k. Proportion of population at time k. Then to get to the next, we say x of k plus 1 equal to this matrix times the previous one. So pretty much we just do that. And to get to the next year, we just take the matrix, multiply to what we have on this year. They just keep doing that. And we don't know that, let's say initially in 2021, so we assume that in 2021, which is x of 0, the note for 2021, we're going to have 0.9 and 0.1. Right, so we do this multiply, give us 2022, and multiply that matrix into the result, give us 2023, and just multiply the matrix, give us to the next year, and just keep doing that. And this is the recursion relation. X equal to x sub 0 meaning in 2021. Right. So this is two of the application that I want to cover here, and we have a lot more application throughout the course. But I do just want to cover this in this section. So I stop the section here. As always, thank you for watching. See you in another video in linear algebra.